The world of physics is an exciting place. You find all kind of mysterious creatures in there, from wave-particle dualities in the lands of quantum mechanics to oceans filled with neutrons or electrons, to futuristic cities powered by perovskite solar cells. And then there are the people that live in this wondrous world. We call them scientists, and sometimes we call them nerds. But this world does not belong only to the scientists. It is also there for you, and science is fun and helps you to better understand the technology and natural phenomena that are around you. I am Lucas, your friendly physicist, and your guide through the wondrous world of science. Now let's start our journey and visit some of these nerdy scientists. I'm already curious what they are up to, and you should be too. With their research, they are shaping not only the future of the physics world, but also yours. The guest for today's episode is Dr. Wei Chen. Wei is an experimental physicist and currently runs the Energy and Photonics Lab at the Shenzhen Technical University in China. Wei started his scientific career in 2006 when he received his Bachelor of Science degree in physics at the Hubei University. At this university, he also got his master's degree, and afterwards he went to Germany to the Technical University of Munich and joined the chair of functional materials to do his PhD. And this is also the place and the time where we both met and became friends. And I really learned a lot from Wei. On the one hand, he was a more experienced PhD student. I think he started 1 year before me or something like this. But on the other hand, he was a real expert on quantum dot materials. And it was really impressive how much knowledge one student can have about a single topic. He was so well informed about all the literature and all the new articles that came out, and he tried things and tried to incorporate different ideas from all over the literature and into his own research. And he went to conferences and talked to people there and really lived the life, I think, the life of a scientist as it should be. And you would always see him in the lab at some photoelectronic device optimizing and fine-tuning things. And then at some point he would come to my office super excited. Hey, look at this. We did it. We finally got the results we were looking for, and it works, and the theory is correct. And there we really shared some great moments together. And it is really great to have you on board of the show because, as said, you are a real expert on quantum dot materials, which is a relevant topic. I mean, there was the Nobel Prize a few weeks distributed among 3 scientists for their groundbreaking research on quantum dot materials. And I know that you were also using their groundbreaking research in your science then. But on the other hand, it's also great that you're here because I finally get to see you again, even if it's only through a screen. But before the show started, we already talked about it. We will definitely see each other next year in March, and then even one time in China in October. And I'm really, really looking forward to this. And I'm also really looking forward to the next, let's say, 30 minutes to hear some exciting stories from the worlds of quantum dots materials. So Wei, thank you for joining the show. How are you doing? And yeah, how is it going in China?
Yeah, it's good. It's also even in Shenzhen, it's start winter now. It's cold outside. Yes, everything at my place is good, but I have to spend too much time on giving lectures. How about you?
Okay. Yes. I gave lectures the last 2 semesters. This semester, okay. I'm not giving semesters. So Christine Papadakis, you know her, right?
Yeah, I know.
She took over the polymer physics.
Okay, cool. My present university have very strong relationship with the universities in also in Germany.
Cool.
Most of them are Hochschule.
Yeah,
Hochschule.
Okay.
Yeah. But the Hochschule is quite fresh in China, so it's still called a university. So
yeah, well, I mean, it's kind of a university, I think.
Yes.
So that's cool. Nice. And I mean, you're a PI of your research group, right?
Yeah, true. But
Uh,
it's really hard for starting up everything. You need to, to join the purchasing and you have to set up all your devices.
mhm,
And also you don't have too many space. This is the
mhm.
main problem. Even though I have a
Okay.
student, but they don't have space for office.
Oh, yeah, I can imagine. I mean, doing super complicated experiments and everything is nothing compared to the task of finding office space or lab space for yourself or for your students. So, yes, all the luck to you for this task, but I'm also sure you will manage somehow. Let's start with the first question. So, a couple of weeks ago, the Nobel Prize in Chemistry was awarded to three scientists, to Aleksey Yekimov, Louis Brus, and Moungi Bawendi, for their discovery and development of quantum dots. And I quote from the Nobel Prize Committee: "Quantum dots is an area of research ripe with exciting results in terms of both fundamental science and present and forthcoming applications." Quote end. Wei, how do you feel about this?
Yes, I feel very excited. Even though I still remember that in 2017, I was give the seminar talk in Peter's group, and
Mhm.
I just give three people, they were all the Nobel Prizes. Two of them are correct, including the Bruce and the Bawendi. So I was so
Okay, cool.
excited. Yes, this means we
Nice.
will probably have more opportunities for higher quality project or the publications. Yes,
Mhm.
yes,
Yeah, I mean, with more publicity and more awareness about this topic, probably it might be easier to get funding, to get
yeah,
cooperations on this topic. Is cool.
true.
We talked a lot around quantum dot materials. Now, of course, everyone wants to know, what is a quantum dot and what is a quantum dot material? Wait, can you give us an answer to this question? A short disclaimer before Wei gives his answer to this question. Whenever Wei speaks of QDs, he means quantum dots. So this is just the common abbreviation of quantum dots.
Yeah, quantum dot is a very special material, but it still belongs to a part of the semiconductor material. Just because QDs actually have older names. It's called like semiconductor nanocrystals. So I
Mm-hmm.
think the names contains like two main properties of the material. The one is semiconductor crystal. The other one is the semiconductor crystal is quite small into nanoscales. Um, I think that the size of the quantum dots are normally like 2 to 20 nanometers compared with traditional materials. QDs are quite magic since the band gap of the QDs is tunable by only changing their size.
So you already mentioned quite a lot of technical terms. Maybe let's dig
Yeah, I'm
into.
so sorry.
No. That's totally fine. It's a science podcast after all, and it's exciting material. So maybe we can dig right into it. You mentioned band gap.
Yes,
Band gap is quite important for semiconducting materials. So
yes,
semiconducting means it's behaving like a conductor, like a metal, but also has insulating properties like a polymer, for example. And semiconductor have a band gap. Can you explain
yes.
shortly what a band gap is and what does it do?
Yes, you mean from the textbook band gap generation can be very difficult, but I will give very brief
Yeah.
very interpretation. I will try my best. And this cannot be very easy, I would say. If you can really understand the free electron gas, and the difference is the free electron gas starts into the semiconductors,
Hmm.
still into the crystals, because periodic structure, I mean, right? And the electron gas starts to to exhibit the scattering effect from the near there's a model to explain this like near free gas theory, and
Yeah.
the electrons cannot exist in certain energy mode. And so this kind of mode, we call this kind of mode like the forbidden region. So this is called band gap.
This is actually a great answer of what a band gap is and how it is generated. Still, I want to summarize your answer for the non physicists among our listeners. So, a band gap refers to an energy range in a material where no electronic states can exist. There, just as Wei said, there these electronic states are forbidden in the context of the free electron gas theory. Now, regarding semiconductors, like our quantum dot materials, the band gap is the energy difference between the so-called valence band. So these electronic states are typically occupied by electrons with a certain energy, and this is defined as the valence band. And then we have the conduction band, which is the lowest energy of unoccupied electron states. So we have at low energy the valence band. Then we have some electronic states that are forbidden. This is the so-called band gap. And then we have the conduction band. And this band gap basically represents the minimum energy that is required to move an electron from the occupied valence band to the unoccupied conduction band. And if this happens, then we have a conducting material, because then we have electrons in the conduction band. If this does not happen, because the band gap is, for example, too large, then we have an insulator. And this is basically the working principle of a semiconductor, where we have both an insulator and a conductor based on how large this band gap is. But instead of bringing electrons from the valence to the conduction band, you are using this band gap in a bit different way, right?
The band gap, actually here we use it for the electrons recombine and emitting specific wavelengths. The wavelength is related to this band gap. If we change the band gap, the emission wavelengths would be different. I would make an instance like the cadmium selenide CDSE quantum dot. If you have fabricate like 6 nanometers quantum dots, it can provide you the red emission. And if you decrease the size of the quantum dots, you will have a larger band gap. Then at this time, you will have a green emission. So basically, you change the size, you change the band gap, and you also change the emission wavelengths. This is how we use the quantum dots. Yes.
Okay, so quantum dots are semiconducting materials, and by recombining electrons within the material, they emit light. And this is what you see then on these famous pictures when you see the presentation of the Nobel Prize and everything, that you have these shiny, bright colors between red, yellow, green, blue, and everything. I will put some pictures and videos of these shiny quantum dot solutions on my Instagram channel. Then you can have a look yourself how this looks like. A side note maybe here, because often this is forgotten. I mean, it's nice to have these shiny colors. Of course, they look nice, but it's also a very easy, let's say, proof of a phenomena that you want to investigate. So it's quite easily detectable, quite easily observable, at least if it's in the visible wavelength spectrum. And if you change the size of the quantum dots, then you change also the value of the band gap. And this defines the emitted wavelength in the end, right?
Yes, indeed. But the difference between the quantum dots and the traditional semiconductor is the QD is actually the size can be changed. And to change it into very specific range, 2 to 20 nanometers, okay? And the traditional semiconductor, of course, you can also decrease the size into quantum dot. This is the thing, but they will, in our daily life, they will not use the in quantum size. They're not in the nano size. They exist like bark or film or something like that. And QDs are used as like a zero-dimension material, because it's too small, just like a dot. But they still can change the size, like varies from like 2 to 10. You can variable. So that means you can change the light emission. You can also change the absorption range. And this is how different I think this is the most part different with the rest of the material. Yes.
So by reducing the size of a classical semiconductor from a bulk material or a film to this, let's call it zero-dimensional nanodot, you can very easily tune the emitted light or the absorbed light if you reverse the whole process. This is the major advantage of quantum dots.
Yes, that's right.
Okay. Cool.
Yes, but you have to mention that if for example, if like the traditional semiconductor have the emission light in visible range, and you change it into quantum dots, okay, then the band gap is quite huge, and the emitting light may be in like ultraviolet. You cannot see it anymore. Yeah, for some specific quantum dots, they have emit the visible light, so people can see it.
But there,
I will make another example. If you
yeah.
increase the size continuously, for example, and the emission light will redshift into infrared and become normal material. It's not magic anymore. Yeah, some material just used in quantum dots is very magic. Yes.
Yeah, it definitely looks very magic.
Yes.
So now we know what a quantum dot is and have an idea how it works. Maybe bring it more to our everyday life. What can we use quantum dots for?
This is a very good topic. I think that's the reason why Nobel Prize committee noticed the quantum dots are very useful. And presently the most useful application based on quantum dot would be the TV panel TV. Okay, so the quantum dots use as I just mentioned, QDs can not only provide green and red, but also provide the green red with very narrow the emission spectral width. That okay, when we define the green, that means okay, I will talk it from the wavelengths. The green should be like besides the green should be besides the wavelengths besides 530 nanometers besides. But if we have a broad emission width, for example, from 500 nanometers to 580 nanometers, that's the broad emission. And the broad emission bring us is not that green. This is the problem. And QDs can provide very narrow emission. It's just within 30 nanometers. It starts from 510 to 540. And this is really green. If you look at some green plant, it's very vivid. We call it like a vivid green, and some are just yellow green. This is different. QDs belongs to vivid green. Yes.
Okay. So you can very precisely tune your color, and this makes a much better quality of your TV screen.
Yes, yes.
The colors.
True. This is how we presently use the quantum dot. But this belongs to those quantum dots as doing the light emitting application. QDs, as I just mentioned, QD can also absorb the light. And this is the one topic in Peter's group, I guess, the quantum dot solar cells. Yes. When you think about the solar cells, it's the benefit. The difference between the quantum dot solar cells and like the traditional perovskite solar cells or traditional solar cells is kind of also different. As I mentioned, QDs can change the band gap. This means QD can absorb the light in infrared range. And this is the traditional solar cells cannot reach. For example, perovskite can only absorb the wavelengths below 800 nanometers. The silicon wafers can absorb the light only below 1,000 and 100 nanometers. But the quantum dots can absorb the light below 1,000 and 800 nanometers. This means we can make this usable infrared energy into the electricity.
So you can harvest more of the solar radiation spectrum and have thereby a more efficient solar cell. Maybe a short disclaimer here. If some of the audience is interested in more detail about solar cells or so, I can recommend episode number 5, where I talked with Leonard about solar cells, which he shot into space. And there he talked a lot about fundamental principles of solar cells, how solar cells are working. Are there different types of solar cells? What are the limits and the challenges scientists are currently doing research on? So it seems quantum dot material is a quite versatile material. You can apparently do a lot with it. Besides building TV screens or solar cells out of it, what other applications do you have in mind? Is there currently emerging trend of a novel quantum dot material application out there?
You can use the QD solar cells can be also used for the infrared photo detection. Is that right? So this is the way we want to go in the future. To use the same configurations but use it for the photo detection, infrared photo detection, and into the panel. Yes.
But then it's not a solar cell anymore, right?
But it still belongs to the similar solar cell structure. It's the same. think about solar cells. Solar cells convert the light into electricity, right?
Mm-hmm.
The photodetector also converted the light into the electricity is the same. You can the working principle is exactly the same. I think this is a very
Yeah.
very promising sort of application, a new promising way for using quantum dots. There's a professor in University of Toronto, Edward Sargent. There's a lot of pays a lot of attention on QD photo detections since 2006, I guess. That was a Nature paper because QD can used for infrared photo detector because the tunable band gap as I
Mm-hmm.
just mentioned. And
Okay.
the QDs are naturally have a very small diffusion lenses for the excitons. Okay.
Mm-hmm.
And this kind of small diffusion atlas can really reduce the crosstalk of between the pixels in the photo detection array.
Okay, I see.
Yes, this is the point. So so this is very low cost solutions for the shortwave infrared detection or camera, because shortwave infrared camera are very expensive. It cost me like 100,000 per one device. But
Oh,
if you
wow.
use the quantum dot solutions, I think the price is maybe just 1% of the price.
So basically, you have a very sensitive, very cheap photo detector in the infrared range. That is quite impressive. Cool. A further question: what are current challenges scientists are working on, or current challenges you are working on regarding quantum dot materials?
Quite actually, the challenges also comes from the property of the material because it's quite small. As I just mentioned, the material have actually extremely high surface area to volume ratio. You can think about the material is just it only has surface, so it is quite sensitive to ambient conditions. For example, like the oxygens and the moistures, and also the bios current. I mean, you put the quantas into like the electricity field, they can also lead to the ions
Mm-hmm.
decomposite. Okay,
Mm-hmm.
QDs to have to conquer such conditions. If the QDs is used for light emitting material, okay, there are very successful solutions for solve this problem by form a core shell structure in quantum dot. Okay, because the light emission part just in core, and outside you can form a semiconductor crystal as a shell, because the shell is not responsible for light emitting. It's just responsible for protect the QD inside. Yes.
So basically, you encapsulate the part where the light absorption or light emittance takes place. And this encapsulation material itself is already semiconducting. Well, that's a smart solution, I would say. That's cool.
Yes. And this is a very successful for lighting emitting applications. But for the solar cells or photodetectors, QDs will suffer very, I would say, they have to enter through a very refined surface chemistry to maintain the performance. Otherwise, they become decomposite or oxidized. And
Mm-hmm.
so this is the challenge of how we use the QDs in the future. Yes, this is
Okay.
challenge. Yes.
But how do you do it? How do you modify surface chemistry? Do you use special materials then, or special treatments, or?
Okay, yeah, that's you just come up with just into my topic directed, my present research topic. Yes.
Ah, okay.
Okay.
So if we now talk about your science and your research, then I think it's time for nerd talk, a real nerd talk. Let me shortly play this jingle, and then let's go. Nerd talk.
Okay. For example, like we fabricate lead sulfide quantum dots, and then we use like a lead how to say it, lead highlights the ions to cape the quantum dot, and then we deposit the films in high concentration. So the QDs are embedded into lead highlight films.
Okay,
So the quantum, yes,
this is like a host matrix which gives
yes,
protection to
exactly,
the,
yes,
and then still the light can penetrate this
yeah,
matrix
true,
and can be then harvested or whatever by
yes,
the quantum dots.
yes, that's true,
Okay. And
yes,
this is your research topic. So
yes,
this is
this is my present research topic,
where
yes.
you work on. Okay, great. You want to talk a bit more in detail about your?
Yeah, that's
Because
no problem. No
yeah,
problem because it's just, I just read too many field papers. I would very happy to share with everyone here. I just
yeah,
followed some recipes as in literature. So I tried and also modify it and also into my own ideas. Okay, this is the principle as you just mentioned, the QD in matrix. This is the structure, how we call the structure. Okay, the problem is now how to modify the matrix. This is the very hot trend in our field. Some people use like lead highlights, for example, like lead iodide, like lead Br or lead Cr, whatever, Cl, whatever. And some other people also use like a perovskite as the matrix. So you can think about it, to put quantum dots into the perovskite from the deposition or from the experiment is very easy to realize. Think
okay,
about the performance of the perovskite is maybe like the anti-solvent method. Okay,
mm-hmm.
you can exactly dissolve the quantum dots into the lead iodide, and
Mm-hmm.
you deposited the films, and it because the precursors already contain the quantum dot,
Mm-hmm.
high concentration.
Mm-hmm. Yeah,
Okay,
yeah,
yeah. The rest is you use the deposition and anti-solvent to realize the formation of the perovskite. This is
okay.
the how is easily to proceed in the experiment.
And then
And
you have a then you have a hybrid quantum dot perovskite film deposited on some
yeah,
kind of
yeah, yeah,
substrate, I
yeah.
think.
Yes.
And the perovskite serves as a host matrix for the quantum dots.
Yes, yes. You can, yes, of course, you have to change the ratio of the quantum dots part and the perovskite part. You have to make the quantum dots part dominate the films, otherwise it becomes a perovskite property. Okay.
Okay, so you have much more quantum dots than
Yes,
perovskite material in the
yes,
film.
yes. The quantum dots can occupy like 70%, even over 70%. So the
Okay.
property of the films is exactly the quantum dot property instead of the perovskite property.
And what
But the
exactly is and what exactly is the task then of the perovskite material?
the perovskite is has a lot of how I would say benefits because the crystal structure is quite very good and much better than the quantum dot. So
Mhm.
the crystal structure of the perovskite can really protect the QDs. This is this is the key point. And the perovskite structure can really fix the surface traps of the quantum dot. Think about it. This is
Ah,
yeah, okay.
okay.
And
So
the third thing is perovskite have a much broad I would say much broad band gap than quantum dot. So this is we call it like type 1 heterojunction. So you can think about it, the perovskite cannot absorb the infrared. So the light can
yeah,
transparent
yeah.
to the films is transparent for perovskite, but for QDs can observe such light.
Okay, and then you use the absorbed light. Then you once again you have a more.
Generate the electricity and to move and to extract the charge carriers. So this is the we call it photo detection.
I see. Cool. Well, then thank you for this amazing nerd talk, and I think then we can officially close this nerd talk by playing once again the jingle.
Nerd Talk.
Yeah, I'm so sorry.
No, 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 no. Don't be sorry.
Yeah, okay,
We're
cool.
we're here for the science.
Yeah.
Great. So, what do you think is this the future of quantum dots?
I would say first to talk about the infrared imaging stuff. Think about this. You know the Elon Musk. Elon Musk just reduced the radar stuff from the Tesla, right? It
Mhm.
just starts to use the full camera system for the autopilot or some other. Okay, this is the problem for the camera, especially in the night and foggy weather, right? You
Mhm.
cannot really see something maybe. But if you use the shortwave infrared camera, that means you can have a very good visions even in bad weather condition or
Mhm.
even in night.
Mhm.
The reasons why the traditional car manufacturers don't use the SWIRE camera because it's quite expensive, as I just mentioned. One camera is cost really a lot. If the QDs can solve the problem, can bring very cheap SWIRE vision applications into the car factory, that would be the future of the quantum dots again,
Mhm.
besides the televisions stuff.
Yeah, it's really amazing how versatile these materials are, and yeah, whoever buys a Tesla, watch out. Maybe your Tesla is packed with quantum dot materials. So, wait. We talked a lot about your materials, but what is next for you?
For me, to be honest, besides to giving lectures in my present university, I also trying to run in my own company to convert such technology into industries. Because I'm now located, my university located in Great Bay Area of China, and there's a lot of car manufacturing here, like BYD, and it is very. I think it is quite famous for the new energy cars.
Yeah.
I already have to have some connections with some they really wants to try the new camera stuff like me. But between me and the car vendor, there was still we have a lot of way to go. For example, like an integrated circuit, I have to deposit my quantum dot into not ITO glass anymore. I have to deposit my quantum dot on the CMOS or some other IC stuff. And to realize the imagine.
Yeah, I can imagine this caused a lot of challenges if you change substrate of your solution.
Yeah. The second one, I have to improve the stability of the quantum dot. As I just mentioned, this is very deadly factor for the material use. Yes. And so my whole team, my graduate student and my postdoctors, they are working on improve the stability of the QD film.
Exciting times ahead of you. I'm very, very happy it turns out like this. Very busy man.
Yes, I have a quite running team right now. I have like 9 graduate students and 1 postdoctor.
Oh, that's great. And still you have time to join me on this show. So I really feel humbled.
Yeah, that's my pleasure. Yes.
That's cool.
Yeah, let's continue. We ask questions or.
I was finished. If you want to add something more to the show, feel free.
No. To me, it's also fine. I'm really happy. I really happy to talk to you. And we have like 2 years not see each other, and this is great opportunities. Yes. One more last thing I want to say that I really miss you guys, and I want to I want to go to Munich as soon as possible and have beer with you guys.
Yeah, I'm really looking forward. I mean, off the mic, you already mentioned this quantum dot,
part, right?
The quantum dot conference next year in March.
Yes. Okay, I will join. Yes.
Yeah, then we see it and we can continue our talk about quantum dots. It'll be nice. I will be in China. I will be in China next year in October to a workshop with I think with Lin and Wei Chen.
Yeah. Okay, I will also join. Cool.
Nice.
Then we will meet you twice next year.
Twice next year. That's really cool.
Can I join it again in the future?
Yeah.
If I have some big discoveries.
Anytime.
Yes, I also expect that. Yes.
Thank you so much. Yes. Take care and say hi to the colleagues. Thanks. Yes, bye. Yeah.
Bye. Have a great day, Lucas.
You too. Thanks.
Say hello to Gear.
I will do it. Bye.
Bye.
That's it for today. If you have any questions left to Wei or me, just let us know in the Spotify comment section below, or you can also always reach out to me on LinkedIn, Twitter, or Instagram. If you like this episode, you might also like episode 5 with Leonard, where we talk about solar cells, or episode 9 with Jill, where we talk about batteries. So both episodes are about, let's say, energy materials, and Wei with his quantum dot solar cells, quantum dot photodetectors also goes in this direction, I would say. And one last thing, this podcast is about you, and everyone can participate. So if you want to share an exciting story about your science, your academic life, some crazy experiments, or any other nerdy stuff, feel free to drop me a short message. Thanks for tuning in, take care, and see you soon on the next episode of Your Friendly Physicist and Other Nerds.